Can you hear me now? Is this better? Yeah, thumbs up. Awesome. Yeah, okay, so what I'll be talking about, I realized that my talk is a slight, the title here is a slight permutation of the title that is on the schedule, but that's okay because we'll be talking about permutation actions, so that's fine. Maybe that was intentional. So in this talk, I will give a combinatorial reproof of some things that some known results, which will strengthen those results and put us on a path towards some conjectures that have not been resolved yet. So when I talk about the background, I will yet again define a matroid. Then I will do Chow rings, and then we'll talk about permutation action. Then we'll touch on what this work was about and see where that puts us in the future when we finish this path. So for me, in this talk, a matroid is defined on a finite set called the ground set, labeled by E, and defined by its lattice of flats. What is a flat? It is, let's take the case of graphical matroids. So those defined by a graph. This is the braid matroid on 4, defined by the complete graph on 4 elements. So if a set of edges is a flat, it must be transitively closed. So the set 1, 2 is not a flat because the induced subgraph includes the edge 5. Where's my pointer? I'll find it one day. Oh, I just did the wrong thing. OK, awesome. There it is. Yes, so the edge 5 is in their induced subgraph. So if I am to have a flat with 1 and 2 in it, I must have 5 in it as well. When I take all of the flats, I order them by inclusion. I get a geometric lattice. I will be talking about the rank of a matroid, which is the rank of the ground set in my lattice of flats. I will denote it as R plus 1 for our convenience. So part of the reason that matroids have maybe seen a resurgence lately is the resolving of these conjectures that had been around for over 50 years for some of them. So this resolving done by DiProsito and Katz, and they proved this conjecture that the sequence of Whitney numbers of the first kind is log concave for any matroid by using the Chow ring and showing that it satisfies the Kähler package. So what is the Chow ring? It is a polynomial ring with a variable for every non-empty flat. So in the case of the braid matroid, it will have 14 variables. It is quotiented by the Stanley-Reisner ideal, which in this case is quadratic, and by a linear ideal that consists of all flats that contain an atom, so a rank 1 element, or an element of my ground set. OK. All of these ideals are homogeneous, therefore my ring is graded, and I can start talking about the graded pieces of this ring. It's not obvious at the moment that the graded pieces only go up to R, but we will maybe see something that will prove this to you or make you convinced. So what is the Kähler package? I won't go into all of the details of it. You can imagine it's quite complicated if it was able to, if it was a powerful tool. But a consequence of it is that the sequence of vector spaces that are defined by the graded pieces of the Chow ring is symmetric and unimodal. So as a sequence, it looks like this. So symmetric, for vector spaces, I mean that I can find a bijective map between complementary degrees, and unimodal, meaning that I can find an injective map from the kth degree piece to the k plus 1 degree piece when k is less than half. I mentioned log concavity earlier. I just want to be clear. Log concavities of this sequence is only conjectured. So I want to work with this ring that has been proven to be a powerful tool. A nice way to work with it is to work with its monomial basis. This basis was given to us by Feichner-Yuzvinsky when they defined this ring, which is very kind of them, to also provide us with a nice Grosvenor basis and a lovely monic monomial basis. So this basis is going to be a product of variables, the support of which is on a chain, and where the degree of each variable is bound by this difference of rank conditions. I'll call these monomials Feichner and Yuzvinsky monomials, and maybe unsurprisingly, degree k monomials provide a basis for the kth degree piece. So let's do an example. We were looking at braid matrix on 4 elements. That's going to be a little bit too small for us to get the picture. Let's do Boolean matrix on 5. I think we can do it, and we'll have a good time. So let's find the Feichner-Yuzvinsky monomials for all of these graded pieces. I only know of one degree 0 monomial that's going to generate the rest. 1, cool. With degree 1 monomials, I should just be able to take the variables, but I cannot take variables that correspond to 1-element sets because if I just have a single variable monomial, that is going to be bound by it has to be strictly less than the rank of the flat, so a rank 1 element cannot have a monomial. Rank 2 or degree 2 monomials, we can get a little bit more interesting here. I can take the square of certain variables, and I can get some chains going, right? Degree 3, I get the following monomials. And degree 4, all I can do, I can no longer increase the degree on anything besides just the single variable xe. Yes, OK. If I want to count the dimension of all of these graded pieces, I get this lovely sequence. Maybe we're feeling happy looking at it. This is the Eulerian numbers. This is a particularly nice sequence, right? It's certainly symmetric and unimodal. Of course, it has many other nice properties. The Eulerian numbers do describe the dimensions of the Boolean Chow ring of the Boolean matroid, but no matter what matroid it is, that sequence is always going to be unimodal and symmetric and observably la concave, though not proven. As I have this up and I say the words symmetric and unimodal, maybe we're starting to see some symmetry in the complementary degree pieces. For example, I have one xe variable here, and I have one xe variable here. I can start thinking about stabilizers and start seeing some symmetry, right? So we talked about this unimodality and symmetry. We said that as the Kähler package shows us these statements about the vector spaces. Of course, that implies it about dimensions. But what we do is show unimodality and symmetry of the monomial basis. So showing unimodality and symmetry of these elements as G sets, G being a group action. So I'm going to take a sip of water, and then I'll say exactly what I mean by G sets. So I want to act on my basis elements. So I'm going to act on them by the automorphism group of the matroid. So we can think of it as poset automorphisms. So we can extend this action on the flats by then we can extend it onto the variables, right? Any poset automorphism must preserve rank, and it must preserve containment, so it will preserve my two ideals, making the Chow ring a representation. even more, these nice qualities that an automorphism must have will also preserve the basis, since the basis is only defined by the rank and containment. And we can see an example here. Let's act on an element, a basis element of the Chow ring on the Boolean matroid of 5 elements, right? I act on it by something in S5. I get something that is still a monomial. So now let's get into our work and let's find these maps. I want to, since I want to map things right equivariantly, I want to map things to things that have the same stabilizer. So I want to, right, I want them to be independent of the group action. So I'm going to define this extended support of a monomial where I just take the support and I add in the ground set, because acting on the ground set will not affect my stabilizer, right? I will define an order on the fiber of this support map, and the order being division, and I can get something like this for a pair of nested flats, F and F prime, where the matroid is of rank 10, and the smaller flat is of rank 3, larger flat is of rank 7. The lattice of extended support looks something like this, where the bottommost element is, maybe as expected, the smallest monomial with the support, and the largest element is just all of these variables, including xc, brought up to the highest degree they can be, where these degrees are, of course, guided by the differences of ranks. A divisor lattice, which this one is always isomorphic to a product of chains. And surprisingly, and these chains are going to be defined by the degrees I can bring up my variables to. Every product of degree chain, every product of chains, which I've cleverly misspelled here, has a symmetric chain decomposition. Let's fix one such decomposition. Then all of every monomial is going to lie in a unique chain. Right? I've partitioned my lattice. And so I'm going to map a monomial that is of k degrees to something else on the same chain. So I'll define a map pi that sends my monomial ak of degree k to something in the complementary degree, which is always possible because my chains are symmetric. And I will send my, then I'll create a map lambda that is going to send things one up in the chain, something like this. And so with this, I get a bijection and an injection of the basis elements, thus proving my theorem. This is probably a good time to pause for questions. Any thoughts? OK. So we've shown this. OK. Let's see what we can see beyond unimodality. So I said the word equivariant. Let's try to be a little bit more specific in defining it. I will say that something is equivariantly non-negative if it is a positive linear combination of irreducible representations. So we saw briefly the braid matroid on 4 elements. As representations, it looks like this. And so I can say that the first graded piece minus the 0th degree piece is equivariantly non-negative because I have 3 copies of the trivial representation, and I'm subtracting only 1. I will also say that things are Burnside non-negative if they are positive linear combinations of permutation representations. And so what we have shown is Burnside non-negativity of the monomial basis of the Chow ring. Unimodality lies at the bottom of a hierarchy that above which is law concavity, and above law concavity is real rootedness. We can formulate conjectures and provide some evidence towards them. We can we can say something about bird-side law concavity and equivariant real rootedness. Again, reminder, okay, real rootedness, law concavity, only conjectured, just. So when I say Burnside law concavity, I mean that I have something like this, right? I can think of it as this inequality, or I can think of it as the determinant of this matrix being Burnside non-negative. Right? And this is strong law concavity as opposed to weak, which weak law concavity is just replacing, it's J and K equal one another, and then I and L are one less and one more. So using our results and the concept of factoring, we can show that if I have a monomial in the J plus K degree, I can always map it into J, set of monomials of degree J and set of monomials degree K, perhaps unsurprisingly. But what this tells us is that for any matroid of rank 6 or less, the sequence is Burnside law concave. And at 7, it's not like this breaks. It's just that I can no longer describe all of my Feichner-Uswinski monomials in this way, where I can just factor them. I mean, we just get degree things. Okay, now equivariant real rootedness. We saw a bit about this in next talk. I will provide this formulation that involves Toeplitz matrix. So we say that something is real rooted if and only if every minor of this matrix is non-negative. I should say I'm mentioning equivariant real rootedness rather than Burnside real rootedness because we have found an example of a 3x3 minor that is Burnside negative. So, of course, I'm working not just with coefficients. I can categorify it. Okay, here's an example of such a minor, right? I can categorify these things to be representations, right? So I can have an infinite matrix of representations, and showing that something is real rooted would involve showing that a matrix like this is positive, right, has a positive determinant. But using the fact that Chow rings are Kazul, which is a recent result by McCullough and Mastroni, we know that every minor that has A1s on the diagonal or A0s on the subdiagonal, just as this one does, all of these minors are going to be equivariantly non-negative. We have also shown that if I have F1 on the diagonal, F0, so degree 1 monomial basis, degree on the diagonal, degree 0 monomial basis, so once on the subdiagonal, I can also create a map of the monomial basis that shows that this is so this one is Burnside positive. And I thought, I was on Google Translate yesterday thinking of how I can say thank you in German, but this is of course, not everyone here speaks German, and I don't want to say this in English, so I thought the most appropriate thing would be to say ciao. Thank you.
Are there any questions?
Hi. Wait. Sorry. Can you hear me? Okay.
Yes.
Can I ask a couple of random questions? So the first is, instead of Chow rings of matroids, I guess Feichner-Uswinski just
Wait,
works
can
for
you say that again?
Sorry.
Slower?
I'm sorry. I'm just really out of it. Okay. So
No.
Okay. So instead of Chow rings of matroids, because Feichner-Uswinski works for like a bunch of things, have you tried seeing what happens on M0 and bar?
On what? Sorry.
M0 and bar.
Oh, yes, great question. So I wish I put in a secret slide. That would have been cool of me. So this does work for, so this whole story that I said works for the maximal building set, but we've also shown that it works for a minimal build, for all building sets. But if I have that, I have to include an extra condition on the group action. So I have to require that the group action not only fixes things set-wise, it also needs to fix my elements point-wise. So if I have that condition, then yes, this is true for M0 and bar.
I see.
Specifically.
Okay, some more random follow-up questions. So, regarding the thing in the verse ring about your like equivariant notion block and cavity, you said you know what happens for rank less than or equal to 6, but have you tried like, any like special like families of matroids? Let's say like paving matroids, or what happens under say like operation like taking minors or like doing hyperplane relaxations and things like that?
So the counterexample we found is of a Boolean matroid on 4 elements.
Okay.
So, so it doesn't work for that.
Well,
I don't have a lot of faith.
all right.
But yeah, great question.
Okay. Well, thanks.
Yeah.
Are there other questions?
I guess my question's just to clarify, to just see if I understand it correctly. So you're saying that a special case of your conjecture is that the rank generating polynomial of the Chow ring is real rooted? Is that correct?
Sorry, can you say that again? I'm just.
I'm just wondering what is just the specialization of this conjecture to like when you're working with numbers.
Oh yeah, so so if I'm working with numbers, it would be that the dimensions of the graded pieces
Right.
do this. Yes.
So that's real rooted. That's the conjecture. And
Yeah,
is that
yeah.
known?
So I guess we're conjecturing something stronger that this is true of the representations, but yes, but not permutation representations because we have a counterexample. Yes, and there are also conjectures about this being just the non-categorification, right? So in terms of degrees, there are also conjectures about it and lots of computational evidence.
So
Yes.
just
Yes.
so even just the real rootedness for just the numbers for the dimensions of the graded pieces that's open as well.
Yes.
Okay.
Yes.
Okay,
Totally. Yes.
Thank you.
Other questions? If not, let's thank the speaker.